In lesson 7.8, we're going to look at indeterminate forms and L'Hopital's rule. So you're going to learn how to evaluate functions whose values cannot be found at certain points. So indeterminate forms are whenever you have forms of functions that when you're finding the limit, they will reduce down to one of these four types. 0 divided by 0, and the thing is that we don't know if that's going to come out to be a 0 or a 1. It's an indeterminate form. Infinity over infinity. We don't know which infinity, if either one, will overpower, because if infinity in the top wins, then it'll go to infinity. But if infinity in the denominator overpowers the top, then it goes to 0. Or it could possibly go to just a single number. 0 times infinity is also an indeterminate form, and infinity minus infinity. All of these are not indeterminate forms, so be careful. Those first four words, these are not. There's actually some other ones as well. So 1 divided by infinity, the limit for that would just be, the answer to that's just 0. Because infinity is really large, and if you take 1 divided by a really large number, it's going to be 0. 0 divided by infinity, that's just 0. 1 divided by 0, and infinity divided by 0. Infinity times infinity, 0 to infinity, infinity to infinity, 0 to negative infinity, and infinity to negative infinity. None of these are indeterminate forms. So if you get something that looks like this, this is not what we're talking about. So what L'Hopital's rule says is that if you are given f and g, two functions, and they're differentiable, and the g prime of x does not equal 0 on an open interval I that contains a, so the limit that you're looking for, as long as g prime of x does not equal 0 there. Then if you're going to take and divide, and you want to find the limit as x goes to a, it's the same thing as the derivative. You can take the limit of the derivatives divided by each other. So one thing to point out, this is not the quotient rule, okay? Not the quotient rule at all. What it is just f derivative of the top divided by the derivative of the denominator. And then you take the limit at that value a again. So something to look for before we start. So some of the ones that we're going to be working on, we're going to have to rewrite it. And so some of them aren't. You can just work them straight up. But we need to rewrite it. When rewriting as an indeterminate product, so when we get to the product ones that we're going to talk about, we try to choose options that lead to simpler limits. So if we have infinity times 0, then we're going to look for an option that will give us a simpler answer. And the reason is that sometimes L'Hopital's rule, it can lead to more difficult expressions to find the limits. So always look for the easiest route. So here's a good chart of all the determinate and indeterminate forms. These are all the indeterminate forms down here that we're going to want to use L'Hopital's rule for. So 0 divided by 0, infinity divided by infinity, infinity minus infinity, 0 times infinity, 0 to 0, 1 to infinity, and infinity to 0. Any of these over here are determinate forms, and you should be able to, in some form or fashion that we've done in the past, find the limits there. So first of all, let's start off with some that we know how to do. Even if we plug in a 4 here, we're going to get 16 minus 16 in the numerator and 0 in the denominator, so 0 over 0. So you're like, oh, that's an indeterminate form. But we know how to do this. What we would do instead of that is that we would factor. So numerator is difference of squares. So we're going to go ahead and factor it as difference of squares. And then we're going to reduce. So even though there's a whole at 4, this reduces down to x plus 4. And then the limit as it goes to 4 will be 4 plus 4, which is 8. Remember, the value doesn't have to exist at a limit. It just has to be able to say what it's going to go towards at that limit value. Another one over here is when it goes to infinity. You would have thought, oh, well, that's infinity minus infinity over 1 minus infinity. And so you're not sure what it's going to go to. whole point on these is, if you can, remember these are just polynomials, you're going to take and divide by the largest exponent. So x squared minus 5x over x squared for the numerator, 1 over x squared minus 3 over x squared, 3x squared over x squared. And you're going to reduce it out. So cancel, this one cancels here with this one. You're left with 4 minus 5 over x, 1 over x squared minus 3. And if you put an infinity in the denominator, that goes down to 0. So we're left with 4 over negative 3, and that's our answer. So the first type of indeterminate form, and indeterminate because we can't determine what it's going to be, the limit at those values, are these. We have the limit as x goes to 0, the sine of x. So the value of sine of 0 would be 0. So this is a 0 over 0. And we can't do that. But there's no way that we can just divide out an x to be able to reduce this down to something we can do. So we're going to take the derivative. Again, this is not the quotient rule. We're going to take the derivative of the numerator. So the derivative of sine is cosine. And the derivative of the denominator, derivative of x, is just a 1. And so then we can evaluate again. I'm going to plug in a 0 here. Cosine of 0 is 1, and 1 divided by 1 is a 1. So my limit of my original function here is equal to 1. And that is not because it's 0 divided by 0. It just happened to turn out that way on this time. The next one, e to the infinity, or infinity to the second, and that would just be infinity over infinity. And so that doesn't help me, but I can take the derivative. So I can go derivative of e to the x is e to the x over 2x. So now we try to plug in again. And so I still get an infinity over infinity. You're like, oh, it didn't work. We can take and do it again. So we can take the second derivative. The derivative of e to the x is e to the x. The derivative of 2x is just 2. So the limit as x goes to infinity. So this would be infinity over 2, which is equal to infinity. So just because it's infinity divided by infinity, that doesn't mean it's going to be a 1. All right, let's look at this one. So for this one, if I plug in a 1 in the numerator, I would get a 0. Ooh. And if I plug in a 1 in the denominator, I get a 0. So that's my indeterminate form, 0 divided by 0. So I can't do it this way. So I'm thinking, okay, well, what if I factor it out? Well, I don't see any way of factoring it out. And then the next thing that I look at is about dividing out the t to the fourth. But I'm not taking it to infinity, so that's not going to help me. I'm still going to end up with the same situation going on. Then if it's to an infinity, if you're taking the limit to infinity, then you can divide it out and the highest exponent, and you can, anything that's left with an infinity in the denominator would be 0. But that's not the case here because it's going to a 1. So I can go ahead and take the derivative of the top and try to use L'Hopital's rule. So the derivative of the numerator will be 20t cubed minus 8t over negative 1 minus 27t squared. So if I plug in a 1 now, I would get 20 minus 8 over negative 28. And that's going to give me a 12 over a negative 28. So this actually goes to a number. And it reduces down to negative 3/7. The next indeterminate form we're going to look at is when we have a product, an indeterminate product. So 0 times infinity, or it could also be a 0 times negative infinity. And we don't know which one's going to overpower. Is the 0 going to be more powerful in this situation, or the infinity? Or is there going to be some kind of compromise in the middle? We don't know. So if we plug in a 0 for this, 0 times what the natural log of 0 is. And of course, the natural log of 0 doesn't exist because remember the natural log looks like this. And we have an asymptote right here, so it never gets to 0. But it's actually going down to negative infinity. So we can use it as 0 times the negative infinity because it's a limit. So the limit is what it's approaching as that number goes to there. And so it's approaching negative infinity. So it's an indeterminate form. So it's a product indeterminate form. So we've got to fix this up. And how you can do this is that you take one of the products and be careful on which one you pick, and you move one to the denominator. And you're like, oh, how do you move it to the denominator? This would be x over 1 times the natural log of x. And so if I want to move it down to the denominator, I can put it as the natural log of x over 1 divided by x. And so that moves it to the denominator. You could also put it as x to the negative 1, which is what I actually prefer to do. X to the negative 1. Because if it changes its place in the fraction, then the exponent changes to a negative. Or you just do the opposite exponent value. So now we can evaluate this, because now we have it in the form for L'Hopital's rule. So the derivative of the natural log of x is equal to 1 over x. So we're still going to find the limit. X goes to positive infinity, or x goes to 0. And then the derivative of x to the negative 1, derivatives decrease. So this is negative x to the negative 2. So what I have now is x to the negative 1 divided by x to the negative 2. And your exponents subtract. And of course, don't forget the negative there. So negative 1 minus a negative 2, that's going to actually just be a 1. So in the exponent. So we have now the limit as x goes to 0 of negative x. And that gives us a 0. So what I did is that because it's an indeterminate form of a product, I need to be able to get it to be a quotient. And I can change it to a quotient by picking something that would be easy to move down to the denominator, like this. Move it down, change the sign on the exponent, and then evaluate it as an indeterminate quotient form. Here's another one. This one would be negative infinity times, and because it's going to negative infinity here, it's going to be times 0, because the graph of e to the x looks like this, and so it's going out and it's going to 0 as it goes to negative infinity. So this is another product indeterminate form. So I need to be able to change it to a quotient. So we always want these to be quotients, because L'Hopital's rule says that you have to divide. So the easiest one to take would be 1 over x. Possibly. Let's see. So this is e to the x divided by x to the negative 1. So the derivative of e to the x is e to the x. And then derivatives decrease, so negative 2 and a negative right here. Well, this is still not going to work. But then I have negative x squared e to the x still. And if I plug in the negative infinity, it's still going to be negative infinity times 0. So that doesn't help me at all. So the e to the x, be careful about it, because remember the derivative of e to the x is e to the x. So let's take it and make the e to the x go to the denominator and leave the x in the numerator. So this will be e to the negative x. And then the derivative of x is 1. Oh, that's actually nice. And then the derivative of e to the x is going to be negative e to the negative x, because you have that negative up in the exponent right there. So we have our chain that we have to take care of. The derivative of e to the x is e to the x, but the derivative of the chain, the negative x, is a negative 1. So now we can plug in that negative infinity. So that's going to be 1 over negative e to positive infinity. And e to the positive infinity, that's going to infinity, so this is 1 over infinity, which is equal to 0. You could have also changed it up right here and said, well, then this is just going to be negative e to the x, and then e to the x. If you plug in the negative infinity there, it's still going to come down here and go to 0. So the next form we're going to look at is indeterminate powers. And so 1 to the infinity, 0 to the 0, or infinity to 0. All of these are indeterminate powers, so you're raising them to these powers. So if we go to infinity, here for this would be infinity to 1 over infinity, which 1 divided by infinity is 0, and taking a limit, so this is infinity to the 0, which is an indeterminate power form. So the method that we do for this is that we need to take the natural log of the function. And so if I take the natural log of x times 1 over x, this exponent comes down in front here. So now I have 1 over x natural log. Oh, did you just see that? I put an infinity there. Natural log of x. And now actually what I have is natural log of x over x. So now I have the quotient again, and that's what we always want to get. We want to get the quotients. So the derivative of the natural log of x is 1 over x, and the derivative of x is just 1 for the denominator here. So now I just need to take the limit as x goes to infinity for 1 over x, which would be 1 over infinity, which is equal to 0. Remember, if you ever have an infinity in the denominator becomes so large that it's going to 0. So look at this one again. E to the x, as we go to infinity, that's going to be infinity and plus infinity, which, well, that's infinity. Infinity plus infinity, still just infinity. But this is 1 over infinity, which is to the 0 power. We can't have that. So infinity to 0 power doesn't work. So we'll take the natural log of the function. E to the x plus x, 1 over x, comes out front, which is ln the natural log of e to the x plus x over x. So taking the derivative of this, let's go ahead and see if I can, yep, yeah, it's all stuck together. Move this out of the way here. We have the derivative of the natural log would be 1 over, and then I have to take the derivative of the inside. So the derivative of e to the x is e to the x, and the derivative of x is 1. And then divided by the derivative of x, which is just a 1. So I'm going to erase that off and see where I'm at. So now what I have is that e to the x, that's infinity, plus 1 over e to the infinity plus infinity. Well, I'm still infinity over infinity, which is still an indeterminate form, so I need to take the derivative again. So I have e to the x over e to the x plus 1, and still infinity over infinity, so taking it one more time, e to the x over e to the x, and that actually just reduces down to a 1, so my answer for this one is 1. So these were the 3 types that we just looked at, and what we did to indeterminate powers is that we took the natural log and we put it in the form of g of x times the natural log of f of x, and we got it to be into a quotient form. You could also do it and write it in exponential and write it that way and take and figure out what your limit is. Either one of these ways are possible. They're options, and whichever way you pick is fine. Alright, looking at the top problem here, if I plug in a 3, oops, I'm going to get 0 over 0. So there's nothing crazy going on here. So I can use L'Hopital's rule, it's indeterminate form, 0 divided by 0, to see what I will get. I could also go and divide an x cubed out of each of them. But we'll just go ahead and use L'Hopital's rule this time. So this is going to be 1 over 3x squared plus 20x plus 31. And now I plug in a 3. And what I get is a 1 over a negative 2. So this is equal to negative 1/2. For this one, second one, if I plug in a 2, I am going to get a negative 1 over a 0. This is not an indeterminate form, so we don't need to take and use L'Hopital's rule. Remember indeterminate forms right here? So on this one, what I'm going to do is I'm going to go ahead and divide out an x cubed on each one of them and see what happens. X cubed, x cubed. So what happens is that I end up with 1 over x squared minus 3 over x cubed all over a 1 minus 10 over x plus 31 over x squared and then minus 30 over x cubed. The problem here is that we're going to a 2 and not an infinity, so really you shouldn't do this. You should look at it and say, well, okay, it's going to 2, that's not going to work. I'm dividing by 0, negative 1 divided by 0. It's not possible, so this one actually the limit does not exist. Now, if we had one single-handed limit, where it came from one side to the other, we could do this, but not for a double-sided limit, because one's going to positive infinity, and the other one's going to negative infinity. Alright, let's look at a couple more, and then we'll be done. So this one would be in the form of infinity times, and then 1 divided by, this would be a 0. Anything to the 0 power is 1. 1 minus 1 is 0. So this is a product indeterminate form. And so in order to do that, we need to go down here and switch it. So I'm going to take this x and divide by it. And then I need to take the derivative. So the derivative of a to the x would be a 1 over x ln of a, and then I need to take the derivative of my chain on the inside. So this is really right here, an x to the negative 1. The derivative of x to the negative 1 would be negative 1x to the negative 2. So that's what I have in my numerator. And this is x to the negative 1. Derivatives decrease. So this will be a negative 1x to the negative 2 as well. And so then what happens is that this right here cancels out, and I'm left with a to the 1 over x ln of a. So this would be a to the 0 power times the natural log of a. Remember, natural log of a is just a number, and any number to the 0 power is just a 1. So this would give me a limit of 1. Alright, we're going to talk about these last two. The last one I'm going to do, but this first one I'm just going to look at. For this one, because of the 1 over x in the exponent, this is when we would do the natural log. And so this will be 1 over x natural log of sine of pi over 2 plus x. And then this x right here in the front will go down to the denominator. And so then we would be able to do the quotient, indeterminate difference. And so that one would be fine. The second one, I don't think we actually talked about it, and I'm not quite sure why. Probably because I messed up. So we're going to do the natural log, 1 divided by natural log of 1. Natural log of 1 is 0, minus 1 over 1 minus 1, which is 0. Remember, for limits, it's possible, so we can do infinity minus infinity. So this is actually an indeterminate difference. So we said that that was one of the things that could happen, is that you could have differences here. For this kind, what you want to do is you want to get a common denominator and try to put them together. So I'm going to start by getting a common denominator. So I need, oops, sorry, let's move this over. I have more room. X minus 1 over x minus 1, the natural log of x, minus the natural log of x over x minus 1, natural log of x. And combine that, I get x minus 1 minus the natural log of x all over. I'm going to go ahead and I actually think I'm going to leave it like that, x minus 1 times the natural log of x. So go ahead and take the derivative of the top and the derivative of the bottom. Again, not quotient rule. This is L'Hopital's rule. Derivative of x is 1. The derivative of negative 1 is 0. And then minus the derivative of the natural log is going to be equal to 1 over x. And in the bottom, I'm going to take the first, x minus 1, times the derivative of the second, 1 over x, plus the second, the natural log of x, times the derivative of the first, which is just a 1. I'm going to simplify this out a little bit. 1 minus 1 over x over distributing this into here, I get 1 minus 1 over x plus the natural log of x. Still not where I want it to be, because remember I'm taking the limit as x goes to 1, so that's still going to be at 0 over a 0. So I need to take the derivative again. So the derivative of 1 is just a 0. And the derivative of x to the negative 1 is going to be negative x to the negative 2 over derivative of 1 is 0. And this h right here is just, I probably should have been putting it up there, that I've taken L'Hopital's rule. So, oops, this will be a plus, because the negative and the negative is a positive. And same thing down here, just x to the negative 1. With that minus in the front, so this is going to be x to the negative 2. The derivative of natural log of x is 1 over x. Alright, so now let's do a little simplifying on this. And let's not forget that we're going to take the limit as x goes to 1. Okay, so this is 1 over x squared over 1 over x squared minus 1 over x. So if I multiply my numerator and the denominator by an x squared, this will give me a 1 in the numerator. And distributing this through, this is going to be a 1 minus an x. Just makes things a little bit easier to deal with here. And so now we're going to take the limit as x goes to 1. So this is 1 over 1 minus 1, which is 1 over 0. And you're like, oh, that's a 0 in the denominator. Exactly. And because it's 0 in the denominator, it's going to be like 1 over 0.00000009, which is equal to infinity. Because it's 1 over a very small number, which flips it and makes it a very large number. So if you take 1 divided by 0, your limit is equal to infinity.